Today I'll be showing you an excitatory circuit made up of just 3 neurons, a short one. We're going to start over here on the first neuron, which is a glutamate neurotransmitter neuron. And so over here there's some sort of stimulus that makes this neuron fire an action potential. Most commonly it will just be EPSPs adding up to send the action potential. And the glutamate that is packaged in the vesicles is going to be transmitted into the postsynaptic membrane and then into this little area here where it's going to bond with AMPA receptors, which are just ligand-gated receptors. So the glutamate bonds to the AMPA receptor, opens up, and it allows sodium ions to rush into the postsynaptic membrane here. And what that does is, if we look at this little action potential thing here, we have millivolts and then we have time. And so the Na+, which is a positive ion, causes the depolarization of the membrane. And once it reaches right about that negative 55 millivolt area, an action potential is fired. And you can see here, there's all these ion-gated receptors that are across the axon. And so when you reach that threshold, the potassium ion-gated cells open, and the sodium ones open as well. And because of the equilibrium potential of each of these ions, the Na will rush in and the potassium will rush out. And the Na is going to have a much higher concentration, so it's going to get right up here to this point. And when that happens, the ion-gated sodium channels are going to close while the potassium ones stay open. They actually open at the same time, but the the sodium ones open and close a little bit faster. So the sodium is going to rush back into the membrane, and it's going to go back down and hyperpolarize, and then you get back to around negative 70. So this is going to travel down the axon to where a ion-gated calcium receptor here is going to open up with this action potential, and that calcium is going to go and bond to synaptotogmin, which is a vesicle protein. Yeah. And what that does is it allows the V snare to connect with the T snare, and the V snare is on the vesicle, and the T snare or target snare is located on the membrane of the neuron. And so the two are going to connect, and it's going to pull the vesicle close enough to where they are going to bond together. And in this case, glutamate, because it's an excitatory neuron here, is going to be transmitted back into the postsynaptic area here, where, since it's an excitatory circuit, is going to once again bond with this neuron here. And just like explained over here, the glutamate is going to bond with the AMPA receptors, the sodium is going to flow in, and then an action potential will be reached, and that will send down to the neuron and continue the circuit.
All right, so I'm going to talk through an inhibitory neurocircuit. So we start with the same way, where the neuron 1 receives some sort of stimulus, where it releases glutamate, which is, as we know from Harrison's explanation, excitatory. So it binds to the ionotropic AMPA receptors, which allows for the influx of sodium. And if sums up to the threshold potential, we will get an action potential, which propagates down neuron 2, which in this case now is a GABA-producing neuron instead of a glutamate-producing neuron. So in the vesicles, we have GABA, which goes through the same process with the V snare and T snare, where the vesicle fuses to the membrane and deposits the GABA receptor into the synapse. Now on neuron 3, we have these GABA A receptors, which are also ligand-gated and ionotropic. And as opposed to sodium flowing in, we have chlorine flowing in, which hyperpolarizes the cell, as we can see here, bringing us further away from the threshold potential for an action potential, which results in no response from neuron number 3.